Thus far, we know how to solve a linear system of equations in two variables by graphing. But as we talked about before, graphing is not an accurate way of solving. So we're going to learn a couple of algebraic methods. One method is what we call the substitution method. Let's see how we can solve a system of two linear equations in two variables by an algebraic method called substitution. Let's look at these two equations. We have x plus y is equal to 6 and y equals negative 3x. Notice this second equation is solved for y. Y is the same as negative 3x. So what if I rewrite this first equation, but instead of y, substitute from the second equation negative 3x, because y is equal to negative 3x. So let's rewrite this equation, x plus, now instead of y, I'll substitute in negative 3x because y is equal to negative 3x. Then finish writing the equation. And now study this equation a moment. Notice we now have an equation in one variable or one unknown. So we can solve this equation for x. What is x plus negative 3x? That is 1 minus 3, or 1 plus negative 3. It's negative 2x, which is equal to 6. And then how do we solve for x? We divide both sides by the coefficient of x, which is negative 2. And we have that x is negative 3. That is the x value of the ordered pair solution of this system. So the x value is negative 3. How do you think we find the corresponding y value? Well, remember, if an ordered pair is a solution of the system, it is a solution of each equation in the system. So to find the corresponding y value, we simply need to choose an equation, let x be negative 3, and see what y equals. And that's what we'll do. Let's now choose an equation of the system. I'll choose this second equation since it is solved for y. If x is negative 3, y equals negative 3 times, again, x just happens to be negative 3, and y equals positive 9. So this system has one solution. The solution is the ordered pair negative 3, 9. How can you check? Let x be negative 3, let y be 9, see if a true statement results there, and also see if a true statement results in the second equation. It will. So by the way, if we graph these two equations, what do we have? We have two lines that intersect in one point, and the one point has coordinates negative 3, 9. We call these then consistent equations, and we have an independent solution or independent equations and consistent system. Let's look at another system of equations. Let's suppose we have 3x minus y is equal to 1 and 2x minus 3y is equal to 10. This is a system of linear equations in two unknowns. I'd like to solve this system. To solve this system, we're using a method called substitution. Now, in our last system, one of the equations was solved for one of its variables. Not so here. But we can make that a first step then in using the substitution method. Choose a variable in one of the equations and solve the equation for that variable. Now, in order not to introduce fractions, you may want to concentrate on a variable that has 1 or negative 1 as its numerical coefficient. So I'm going to choose this equation and I'll choose that variable since its coefficient is -1. So let's go off to the side. Here's my equation. How do I solve that for y? It's up to you, but if you'd like, we can add y to both sides. If we do so, we'll have 3x is equal to 1 plus y, and then I can subtract 1 from both sides, so I'll have 3x minus 1 is equal to y. However you want to do it, I have this equation solved for y. So let me write it off to the side. Y is 3x minus 1, or 3x minus 1 equals y. I've solved that equation for y. Now, how does the substitution method work then? I will write down the other equation, and instead of y, I'll write 3x minus 1. So make sure you write down the other equation. I will write down this equation. Now be very careful. 2x minus 3 times, instead of y, I will write 3x minus 1, and then finish, is equal to 10. Now I have an equation in one variable. Let's go ahead and solve it. 2x, be very careful here with the distributive property. -3 times 3x, that's -9x. I'll write minus 9. And then -3 times -1, that's positive 3. I'll write plus 3 is equal to 10. Got a few like terms there. 2x minus 9x, that is -7x, plus 3 is 10. Let's now subtract 3 from both sides, and I'll have 10 minus 3, or 7. And then divide both sides by the coefficient of 7, and I'll have that x is -1. This is the x value then of the single ordered pair solution of this system. So thus far we know x is -1. How do we find the corresponding y value? You can choose this equation, you can choose this equation, which is equivalent to this one. It is up to you, but choose one of the equations that has both variables in it, and let x be -1. All right, so I'm going to choose this one since it is already solved for y, but it certainly makes no difference which one you choose. If x is -1, I'll have 3 times -1 minus 1 is equal to y. 3 times -1 is -3, minus 1 is -4, and that is y. So y is -4. What does that mean? The solution of this system is this ordered pair solution. How can you check? Let x be -1, y be -4 in this equation and also the second equation. And what's the appearance of these equations? We have two lines that intersect at the point with this or these coordinates. So we have independent equations and we have a consistent system. Let's now look at some steps we can use to solve systems of equations by substitution. Step 1, solve one of the equations for one of its variables. Step 2, substitute the expression for the variable found in step 1 into the other equation, and that's very important. Substitute it into the other equation. Step 3, solve the equation from step 2 to find the value of one variable, and then step 4, substitute the value found in step 3 in any equation containing both variables to find the value of the other variable. And then step 5, check the proposed solution in the original system. Keep those steps in mind and let's solve another system of equations by the substitution method. By the substitution method, We pick one of these equations and one of its variables and solve. Now, I told you earlier to look for a variable whose coefficient is 1 or -1 so that you don't need to introduce tedious fractions. Well, we don't have such a variable here, so I'm noticing that all of these coefficients and that constant, those are multiples of 3. So let's go ahead and choose, say, equation 1, and I'll choose x. But there are certainly other ways of solving this system by substitution. So I'll choose this equation. I am solving for x. So I have 3x plus 6y is equal to 9. I'll subtract 6y from both sides. So I have 3x is equal to -6y plus 9, or 9 minus 6y. And then I will divide both sides by the coefficient of x, which is 3, -6y plus 9, all over 3, and this right side will simplify. Now remember, this 3 goes with each of those terms in the numerator. What is -6y divided by 3? That's -2y. And then what is 9 divided by 3? That's plus 3. I have solved for x, and luckily each of those coefficients were multiples of 3. All right, so x is -2y plus 3. Now what do? I substitute this expression for x in the other equation. So let's go to the other equation. I'm going to write down the other equation. Now instead of x, what do I write? -2y plus 3, and then plus 8y is equal to 16. And now we solve this equation for y. Let's use the distributive property. That is -8y plus 12 plus 8y is equal to 16. -8y plus 8y, that's 0y or 0, and all the variable terms subtract out. I end up with a false statement. Now, what did that mean when we were solving linear equations? Not systems, but linear equations in one variable. If we ended up with all variable terms subtracting out and a false equation or a false statement, that meant the original equation had no solution. Not unlike here, it does mean that this system has no solution. These are independent equations, but this is an inconsistent system. Thinking about the graphs, how can two lines then end up not intersecting? Because if they did intersect, we'd have a solution to the system. These two lines are parallel lines. They don't intersect. That means this system, which we have solved algebraically, has no solution. So there's a special case, just happens to have no solution. Let's look at another system of equations. Let's suppose I have, say, 1/3 x minus y is equal to 2, and say x minus 3y equals 6. There is my system of two linear equations in two unknowns. I'd like to solve this by the substitution method. So we'll choose one of the variables in one of the equations, this one or this one, because the coefficient is 1 or -1. I'll choose this equation. I will solve it for x. Do you see that since I have x minus 3y is equal to 6, then x is 3y plus 6, or 6 plus 3y. It makes no difference. So from there we have that x equals 3y plus 6. Now what do I do next? I substitute the expression for x in the other equation. That's the important part. So here's my other equation. I do have 1/3. Now instead of x, I will write 3y plus 6, and then minus y is equal to 2. Let's now solve this equation for y. Luckily, we again have multiples of 3 here, so 1/3 times 3y, 1/3 times 3 is 1, so I have 1y, or simply y, and then 1/3 times 6, that's 6/3, or 2, and then minus y is equal to 2. Now notice what happens. Y minus y, the variable terms subtract out again this time, but we end up with a true statement. Remember what that means when solving a single linear equation? When variables subtract out and you have a true statement, it means that the original equation has an infinite number of solutions. We usually say all real numbers. Well, that's similar, not quite the same, but it's similar to what we have here. Since we have a true statement and all the variable terms subtract out, we do mean that we have an infinite number of solutions. Actually, it is true that these are what we call dependent equations. It is a consistent system, but these are dependent equations. If we graph this equation and then we graph this equation, the graphs are identical. So since they're identical, they intersect in an infinite number of points. Now, not just any ordered pair is a solution. If an ordered pair is a solution of this equation, it is a solution of this equation. So any ordered pair solution of this one is a solution of this one and is thus then a solution of the system. But this is a case where we have an infinite number of solutions. At this time, practice solving systems of two linear equations in two unknowns using the substitution method. We just reviewed the substitution method for solving a system of linear equations in two variables. Let's see how you are doing by answering the following question. If a system simplifies to 0 equals -1 when solving, how many solutions does the system have? Does the system have one solution? That's choice A. Does the system have no solution? That's choice B. Or choice C, does the system have an infinite number of solutions? The video will pause, take a moment, and then make your selection. Choice A is incorrect. When you're simplifying a system and you have a false statement and all variable terms have subtracted out, that means the system has no solution. The correct choice is choice B, no solution to the system. Choice B is the correct choice. If when simplifying, all variable terms subtract out and you end up with a false statement, it means the system has no solution. So choice B is the correct choice. Choice C is incorrect. When simplifying, if all variable terms subtract out and you end up with a false statement, that means the system has no solution. Now, if variable terms subtract out and you end up with a true statement, such as 0 equals 0 or -1 equals -1, that does mean the system has an infinite number of solutions. But for this, that is incorrect, And the correct choice is choice B. The system has no solution.